you did sign your paper. Chemistry time, we have to say chemistry time. Say it.
Chemistry time.
Thank you. Okay, anyway, we've already begun chemistry, actually. We talked about scientific notation, but I forgot to film it. We talked about the SI, which stands for, nicely, the International System. SI, that's how abbreviations work, don't at me. Okay, there are 7 base units in the SI. We in chemistry mostly talk about 5 of them. The other 2 are amperes, which measure electric current, and candelas, which measure luminous intensity. I'm positive, I know there are disciplines within chemistry even that do use those, but these are the main ones we will use. These are the ones that we will use in this class, so those are the ones we need to know. Is this all the units in existence? Obviously not. What's something that's not on here that is in the SI that you remember from your lab? What unit did you use?
Milliliters.
Milliliters, yeah. That's a volume unit, which is actually derived from meters. 1 liter is actually a cubic decimeter. This is the definition of what a liter is, and then obviously the milliliter is based off of that as well. What's this mean? Deci. What do we call this little thing that's in front of the unit, though? A
prefix.
Prefix. Here's some prefixes you need to know. The most important ones, I would say, that come up the most often, at least in my experience, are lowercase k, which is kilo, which means 1,000 times. Lowercase m, which is milli, which means 1/1,000th. Do you see the difference between those two things? Because this is something that really confuses freshmen lately. Many of them are having great difficulty, aren't they? Aren't they, Alexis? What's the difference between 1,000 times something and 1/1,000th of that thing? I mean, what's the difference between those two things? Not mathematically, but conceptually. This one is making the quantity smaller. This one is making the quantity larger. Yes. And some other ones that come up somewhat frequently. Lowercase d is deci, which means 1/10. Lowercase c is centi, which means 1/100th. Capital M is mega, which means 1 million times. Capital G is giga, which probably means what?
Billion.
1 billion times. A million is 10 to the 6th. A billion is 10 to the 9th. Which makes me realize that this is actually 10 to the 8th up here. Ignore that. And then some of the other ones that we use are the smaller ones. Nano, micro, pico. We don't use pico very much in this class, but it does come up in chemistry. Nano is 1/1,000,000th. So 10 to the -6th. Micro is 1/1,000,000th, which is 10 to the -9th. And then pico is 1/1,000,000,000th. And the reason that I bring pico up is because we use it in meters, especially because a picometer turns out to be a pretty close to or it is a useful measurement when we're talking about atoms and molecules, picometer. This little thing just BT dub. Here's another Greek thing for you. Micro is the lowercase Greek letter mu. You can look it up, but unlike the rho, what I've drawn here is actually a pretty accurate representation of what the Greek lowercase letter mu looks like. It's also in your book. On page 33, you can see the little Greek mu is a symbol there. It's italicized because in textbooks like this, foreign language things should often be italicized. Glaringly, obviously, on the next page next to it, the Système International de l'Unité is not italicized, but it probably should be. Some very common temperature conversions that you're going to need are, for temperature here, are Kelvin to degrees Celsius. All we have to do is add 273.15. And then what if we were going from Celsius to Kelvin? Subtract 273.15. Other than this, there's also a Fahrenheit conversion, but other than this, all the other conversions are what we're going to work on for the rest of the day. The book does talk about density, but guess when we talked about density? The last chapter. So we're good on density. You told me you're good on scientific notation. I'm going to talk about one more thing two more things. 3 more things before we go to the meat of this, which hopefully we can still get done today. So we're going to talk about those 3 other things very quickly here. Questions on the Système International. Is this all the information you'll probably need for your test? Probably not quite. I would say this is the lion's share of it. Where can you find the remaining information primarily?
When you read your chapter.
When you read your dang chapter. Thank you, Kyla Vogel. Thank you, Kyla Vogel, star of the video. When you read your chapter, but also, what else if you need some additional information? Do you think this is private knowledge only to those of us in Crawford? No. The internet is full of information about the Système International. You can also watch the video that I did of this last year, which may exist and it may not because I might not have been filming it. Okay, let's move on though. Questions about any of this? Does it need to stay up there? Okay, then it won't. Everyone's got all this.
Wait. Not the, don't erase the Kelvin to Celsius part.
I almost did though.
I know.
Okay, so the next thing we're talking about is accuracy versus precision. So write that down, please. Accuracy versus precision. Does anyone ever shoot anything? You don't have to be too specific. I don't want to have to turn you into the police. Does anyone ever shoot anything though?
Yes.
Yeah, you've all handled a firearm, as it were.
Yes.
Accuracy. I figured you probably would have, but this is the Wild West, versus precision. So pretend we have a target. This is what targets look like to me. We're going to have 3 targets here. Those are actually pretty good, if I do say so myself. Accuracy is how near. This is all a metaphor. I mean, it is true for firearm shooting, but this is not firearm shooting class. But accuracy is how near the hole, the bullet hole, the subject of our discussion is to the truth, to the center of the target. Okay, so metaphorically, it's how close our values are to the actual truth. What would it impact accuracy?
How many times you get in that spot?
Yeah, exactly. So in shooting, you need to get it it's how close they are to the middle is the accuracy. Precision is how they're grouped. Grouping. But the accuracy is the nearness to the truth, the center. Precision is the grouping. So maybe you're discharging a firearm, as it were, and you shoot it. That's the sound it makes. You have a silencer on it. You're like, nice, perfectly accurate. And that's true, isn't it? It's perfectly accurate. You shoot it again, and there it is. So, was the first one accurate? Yes, the first one was accurate, but were you precise? No, and that's the difference here. Precision is about grouping. Whereas the next guy comes along, and he's better than you. You know how it is. He's better than you, and you're like, you stupid loser. You can't even get it in the middle. But then he shoots the rest of them, and they're like that. And none of them is perfectly accurate, but he's more precise. You see what I mean? So metaphor. This is a metaphor. What we're talking about in science is that for the data to be accurate means it's close to the truth. And for it to be precise is that it's all grouped neatly. They're within a certain range of each other. So when on their lab, was it you, Kyla, and who was your partner? Alexis? Was it you guys that had the outlier?
Yep.
Yeah, you had an outlier on your data. It was an order of magnitude. It was 10 times what the other ones were. And that's an outlier because it lacked precision, right? Maybe the other ones were accurate. Maybe that one was accurate. It's hard to tell. But precision is how close they are together. And accuracy is how close they are to the truth.
The outlaw.
The outlaw. Speaking of discharging firearms. You have questions about this? This is all a metaphor. It is used in target shooting, this terminology. But you understand what it means for data collection. Questions? Okay. So what we do with that is another thing called error calculation. So write this down, please. Error calculation. That wasn't very precise. I mean, error calculation. Oh no, I'm running into where I just erased. And percent error. This is fairly easy, but error, what we call the quantity error, is equal to the experimental value minus the accepted value. What would be experimental value in our case? The lab I'm talking about. What was the experimental value for your density? Yeah, what you found the density to be. And what would the accepted value be?
Whatever it actually
The truth of what the density of that object is. And then from this we can calculate percent error, which is equal to the absolute value of the error over the accepted value. Whoops. Basically, this is telling you how wrong you are. And the reason we have a percent error, do I need to rewrite this so it's more legible?
A little bit. What does the top one say there?
Percent, or it's the absolute value of error, which you calculate using that formula above. The reason this is more important than this, the reason percent error is more important than error, is that if I tell you that my height is 6 feet, and I'm an inch off, either direction, I don't know what it is, but if I was 6 feet tall and I'm an inch off of that, my error is 1 inch, right? Now, if I were talking about the length of a Lego brick and I was an inch off, that would obviously mean much more, right? Because a Lego brick is smaller than I am. Alternatively, if I'm talking about the Eiffel Tower and I say, oh, it's 300 feet tall, I have no idea how tall the Eiffel Tower is, but if I say the Eiffel Tower is 300 feet tall and I'm wrong, which I know I am, however much I'm wrong would matter more if I was that much wrong talking about a human being, right? If I'm 50 feet off of the Eiffel Tower, that makes less of a difference than if I'm 50 feet off the height of Mr. Snitley, right? Do you see what I'm talking about? So we use percent error because the percent error compares how wrong you are to the total value. If I'm an inch off in my description of the length of a bridge, that means less than if I'm an inch off in my description of the length of a caterpillar.
Is that a times 100?
Times 100 to make it a percentage. This is calculated, if you think about it, the same way that you calculate your test scores, or that I calculate your test scores. It's your amount divided by the true amount, times 100%. So if you got 40 out of 70 on your test, 40 divided by 70 times 100 is your percentage. Okay? And now this is where we still have a little bit of time, so we're doing fine. We're doing fine. We're gonna just have to get through 2 more things. And here they are. The first one is sig figs. Write it like that, and then in parentheses I'm gonna write what it stands for. Significant figures. Figures, we say in America. Sig figs, significant figures. This answers the age-old question of the freshmen doing their conversion worksheet. Do you want me to round it to the 2 decimal places? They always say things like 2 decimal places.
This is my trig class.
Good. You can help out your homies then. They're always asking me, 2 decimal places? Because they don't ever want to say things like hundredths, because God forbid they be right or correct about anything. But this tells us how to get from our given how many decimal places we should go to, is basically what this is telling us. So we always use the number of sig figs in our answer as the least amount in the given. Basically, you've heard the thing, a chain's only as strong as its weakest link, right? It's the same thing. Our answer can only have the precision of the least precise value that we used in calculating that. So here's some rules are non-zero digits are always significant. That one's easy. So basically, of the 10 digits, the only one that we ever have to have any kind of consternation about is a 0. Zeros are significant if they are I'm going to do this pose, between significant figures, or if they are after a decimal and after a sig fig. Sorry, that got kind of windy at the end. Non-zero digits are always significant. Fine, easy. That'll never pose a problem to you. Zeros, though, are significant if they're between other significant figures, or if they're after a decimal and after a sig fig. So let's look, I'm going to give you a few examples here. Straight from your book. How many significant figures? 3. Super easy. 1, 2, 3. They're all non-zero. What about this one? 3, because the 0 here is between significant figures, so 2 is significant. What about this one? 1. Only 1, because these other zeros are not to the right of a decimal, and they are not between significant figures. 3, 2, just 2. Remember, they have to be to the right of a decimal and to the right of a sig. I put after here. After a decimal and after a sig. So this would have 3, because this is to after a sig fig and after the decimal. Basically what it's doing is it's telling you, just like I talked about in the lab, this 0 tells us we measured the 10,000th place and found that it was exactly 0. In this one we only measured to the 1,000th place. Does that make sense? These all indicate precision. This one might have been rounded from 550, it might have been rounded from 599, it might be exactly 600, but it can only be this precise as the hundredths place, okay? And the more you practice these, the better you get at them, so that's why you have a heckin' chapter review to do, okay? Do the chapter review by Monday. No, Friday. Phew, we'll have the test Monday. Do the chapter review by Friday. We'll have the test and the polyatomic ions will be on Monday, because tomorrow we're going to talk about something called dimensional analysis, which I also call unit conversions. And it shouldn't take us very long because I think you've all had it already, but we do need practice on all of this. And as Kyla directly or astutely points out, it is kind of a lot of work for one class. So, questions about any of this? So, scientific notation? Yeah? Significant figures? Yeah? The Système International d'Unité? Yeah? Prefixes?
C.
Oh, C, yeah. And error calculation. That's what we did today. That's kind of a lot of stuff. That it is. It just means if. Which is not really an answer to my question. 5. Okay.